This is section 12.2, graphing rational functions. What we're going to do first is look at the parent function here. The parent function is y equals 1 divided by x, and here we're going to assume that the numerator and denominator are polynomials. And of course, x cannot be equal to 0 or it would be undefined. If you take a look at the graph, as we pull this down a little bit, you'll see that because it's positive, that the graph's in the first and the third quadrants. The horizontal asymptote is the x-axis, and the vertical asymptote is the y-axis. Those are the two lines, horizontal and vertical, that the hyperbola hugs. So you're going to see that they just follow that curve. They will never cross the asymptotes. This is really important, so that later on when you start to drop the asymptotes in, know that your hyperbola will be in 2 of the 4 quadrants, always on the opposite side, so diagonally, but they will never cross those asymptotes. So once we have that parent function in, and you'll see here that the parent function is red, we're going to compare this new function y equals negative 2 divided by x with the parent function to see what that negative 2 does to it. Well, what happens is multiplying by negative 2 makes the graph a vertical stretch of the parent. That means it's going to be bigger and wider, right? Like with the graphs we looked at in the last chapter. But it's also a reflection of the original. Look and see that it is now in the opposite quadrants because of that negative 2. So you're looking at the blue graph here. So it's in quadrants 2 and 4. This is something that's going to consistently happen. When that numerator is positive, your hyperbola is going to be in quadrants 1 and 3, and when it's negative, it will be in 2 and 4. Let's take a look at this one. Y equals 1 divided by 3 times x. So what does it do when you put a 3 in the denominator? Well, it's going to make y less, right? It's going to decrease that value of y. So this becomes a vertical shrink of the parent. Again, on this graph, the parent is red, so that's our original graph. The new function is in blue, so you can see how it's lower and it hugs the asymptotes a little bit closer. Now we're going to get a little more complicated. We're going to add a constant on the end of the equation. So we're going to graph y equals 1 divided by x, that's our parent, right, plus 3. Then we're going to identify the domain and range and compare it to the function. So the easiest way to do this at the beginning is to make an input-output table. Make sure that you have positive and negative values for x so that you can see what it does on both sides of the y-axis. So here I went from negative 2 to positive 2. Okay, at 0, the function is undefined. So if you take a look up here, you can see that x is in the denominator, so 0 is going to make it undefined. Those are my points. Then down here I graph the points. Now the red graph is the parent function, so I kept that there. The points from the input-output table have been plotted in blue, as you see on the graph, and then I connected them in green. The domain here is all real numbers except for 0, because 0 makes it undefined. And the range is all real numbers except for 3. Okay, it's hugging around 3. The graph is a vertical translation of the parent. Vertical translation, that means it's shifting up. That's what adding 3 does to the graph. It moves it up. So if you think about this logically, if I was subtracting 3, what would it do? It's going to move the graph down 3, right? So it's almost like you're adjusting the y-intercept in a line. You're moving it up and down on the coordinate plane. And you can see the difference with the parent function here. Okay, the parent function hugs the asymptotes of 0, 0, but you can see this is definitely on 3 and 0. You could draw a horizontal line straight across 3, and neither branch of this hyperbola would ever cross that 3. Now we're going to graph y equals 1 divided by x minus h. This is different because the constant isn't being removed or added at the end after the fraction. It's actually in the denominator. So let's see what this does to the graph. We're going to graph y equals 1 divided by x minus 2. Again, you will create an input-output table and identify the domain and range. Now when you look at this, in the denominator, if x were 2, the function would be undefined. So x cannot equal 2. That means the domain is all real numbers except 2. The range is going to be more obvious when you start to look at the input-output table. So we'll pull that down. Here's my input-output table, and you can see the values of y here. At 2, x is undefined. That's right here. So let's write that in. Okay, so you can see that the graph is green. Because the numerator of the fraction was positive, it's going to be in the first and third quadrants. The asymptotes here are 2 and 0. You can see how it hugs that vertical line of x equals 2, right? That's because the domain was all real values except 2. So this graph can never cross 2. It's going to go on either side of it. The points I plotted are in blue again, and the graph is in green. This key concept is what we're trying to get to you throughout this whole section. This is what we're working up to. And it's telling you that you can graph these rational functions if they're written in this form, that is y equals a divided by x minus h plus k. And here a cannot equal 0. By using the values of a, k, and h, these values are all really, really important, so you have to recognize them in an equation. This is always a hyperbola, first of all. Okay? You can set the horizontal asymptote as y equals k. So look at the number that's being added to the end, and that becomes the horizontal asymptote. The vertical asymptote is always x equals h. Okay, so go down into that equation. Now what's key in this equation, though, is in that denominator, it has to be in the form x minus h. Okay, so be careful. When something's being added in that denominator, you actually have to reverse the sign. The domain here is all real numbers except the h, and the range is all real numbers but y equals k, because you have to remember what those variables mean, right? Those are the asymptotes, so of course they're not going to be included. So here's an example written in that form. We're going to graph y equals 2 divided by x plus 1 minus 3. So the first thing you do is identify the asymptotes and drop them on the graph. And we usually do this with dotted lines so they stay separate from your hyperbola. So if we look at this, the vertical asymptote is going to be negative 1 because it has to be in the form of x minus h here. And so this has to be a negative 1. And the horizontal asymptote is going to be negative 3, right? So we're going to drop those two lines, and I did them in hot pink so that you could see them. Then what you want to do is test several points on either side to see in what quadrants this hyperbola is. Remember, a hyperbola is always in 2 quadrants, and it's always on a diagonal opposite. So you could have taken a guess by looking at this equation that because 2 is positive, it's going to be in 1 and 3, and you actually would have been right. But I plotted a couple of points to see that it actually ends up in 1. So I roughed in my hyperbola on both sides, and that's all you're going to be asked to do. What you really should be concentrating on is setting up where the asymptotes are, because once you do that, you can easily fill the graph in. Here's the second example. We're going to graph y equals 4 divided by x minus 5 plus 6. Again, drop the asymptotes first. The horizontal asymptote is 6. Remember, that's always the number that's added onto the end. And the vertical asymptote is 5 because it's already in the form of x minus h. So the h is 5. So you're going to drop that in. Again, I did it in hot pink. And test points in all 4 quadrants. Once you see that one works, if it's working in the first quadrant or the upper right-hand section, where you've divided it with your asymptotes, then you know that's where the graph has to go. So I just roughed it in with green into the first quadrant and the third quadrant. And again, it hugs the asymptotes. So we're going to look at a word problem now, okay? Because you want to be able to use this in a real-life situation. You don't usually go around drawing hyperbolas. So you're looking at an art club planning a bus trip to a museum, and the cost of renting a bus is $495, and we're going to divide this equally among passengers. In addition, Anyone who's on the bus has to pay for a museum ticket that costs $12.50 per person. So the first thing we have to do is write an equation that gives the cost C as a function of the number of people, P, going on the trip. Then we're going to graph and describe the changes in C as P increases. In other words, how does each person's cost change as the number of people on the trip increases? That's sort of a logical question you should be able to figure out before we graph this. And then you're going to use the graph to approximate the number of people who need to go on the trip, because we want to keep the cost to about $25 per person. So we're going to look at this equation. It's C equals 495 divided by P plus 1250. You take the cost divided by a person, and then every person has to pay the $12.50 to get into the museum. You can graph this on your calculator. Okay, the horizontal asymptote here is 1250. We know that from our equation, and the vertical asymptote is 0. The graph is going to be in quadrants 1 and 3 because the A is positive. You see how that 495 is positive? That's going to throw your hyperbola into 1 and 3, again, diagonally opposite on the coordinate plane. You can see from this that as you increase P, because it's in the denominator, the C is going to decrease. Okay, that makes more sense, right? The more people you have on this bus, the less it's going to cost per person. You just have to cover that $495. So if you have 10 people on the bus, it's going to cost them $49.50 each, right? But if you have 50 people on the bus, it's going to be a fifth of that. If you want to keep the cost to $25 per person, you want to set your Y, or your C, equal to 25 and solve for your P. Now you could do this. You could also use the graphing function on your calculator. So go into Y equals, type the equation in, and after you see the equation on the screen, press the trace feature, and then you can follow the point along till you get to where you want it to be. Okay, adjust the Y value to 25, and then you'll see what the P value has to be. It ends up to be around 40 people. So you need 40 people on that bus to keep the cost to $25.